XML object that you're trying to instantiate. Well, you don't necessarily want to put that string directly into your script because there may be security devices in line that are looking for the instantiation of some XML class or a particular exploit code. So you can simply split that content payload up any way you want and have that string concatenated throughout the script dynamically during interpretation or runtime. And naive approach to content filtering in line is going to miss these kind of things because there's literally infinite ways that you can string concatenate your desired payload together. A few other obfuscation techniques to look at. Integer obfuscation. If you have a particular number that you need to use in your exploit, you would be rather naive just to have that number defined in the script. There may be some security mechanisms that are looking for that particular content. Well, just like we showed with strings before, there's infinite ways you can add and subtract and multiply and divide and use just basic operations to eventually yield a variable with the integer value that you're looking for. And here, the example is just, here's one way to encode 31337. You could obviously get much more sophisticated using mathematical operators or bit shifting and things of that nature, hex values, that will kind of throw a monkey wrench in the whole inline security device that maybe takes a naive approach to looking at these things. I recommend y'all check out Alexander Sotorov's talk tomorrow on JavaScript heap spray, and or as he terms it, JavaScript feng shui. Basically, the idea there is that your JavaScript, since it's being interpreted dynamically in the browser, all that execution is affecting the heap of the browser, the memory space of that application. So, if you're trying to exploit the browser for whatever purpose, you may spray trampolines or exploit code, or depending on your exploit, across the entire heap of the browser. And then it's kind of like, you're setting someone up for a 1-2 punch. You essentially spray your code, your exploit code, your trampolines, whatever, across the heap, and then you follow up with the exploit and you jump into that memory area. So once again, the dynamic interpretation of this stuff in the browser is really making the security of that application more brittle. And one interesting aspect of JavaScript is it's so dynamic. Variable names, function names, class names can all be redefined as many ways as you like. So just because someone is calling document.write or some normal function, CHR, earlier in a script or in another script that's been included, they may have redefined that function. It may actually be evil hacker's function, yet in that script it's simply CHR or write. And so, one of the power of JavaScript is it's so dynamic and you can redefine everything, but that's also a big weakness from a security perspective, because if you're looking simply at the syntax of that script, you're never quite sure what the real meaning of those variables or functions is, because they could have been redefined at any point prior in that execution. More sophisticated technique we've seen is block randomization. And so you can imagine if you're trying to achieve some end in your script, you can basically wrap it up in a variety of for loops or while loops or do while loops. Sometimes they may actually work out to be essentially a no-op. They don't do anything. They're just simply to fool the analyst or to throw off a security device. But it's much more sophisticated and difficult for a security mechanism to really unwrap those loops and unravel those loops to determine what this script is really doing, short of actually executing it. And that's not always a feasible approach for an on-the-wire kind of prevention device, in that the latency or the resources involved in trying to dynamically interpret these scripts on the wire can be a real challenge. So frequently you see attackers combining all of these techniques together, and that really makes the job of an analyst much more difficult. They may have while loops that including the while loops, they're doing string encoding in that loop. And maybe they're adding some variables together, string concatenating or integer addition within these loops. And then they're using some Unicode encodings. So short of having some automated tool to do this, it's very difficult for an analyst who has a sample of JavaScript and is trying to either do an incident response or determine what this script is. Is it malicious? Is it benign? It's really challenging unless you had some automated tools to tackle this stuff. And right here, this is just an example of a script, a malicious JavaScript that we were provided from a researcher. And if anyone, by the end of this talk, tells, or by the time we get to the slide that reveals what this is, if you can tell us, raise your hand and I'll buy you a beer. It's very ugly. You could see use of toString. You could see replacements, hex values. It's a real mess. But this is something that was found in the wild, and this is a real example of something we consider highly obfuscated JavaScript. And obviously when you're dealing with something like this, you really want some automated tool. You don't want to sit down and try to figure this out on your own.
So enter Caffeine Monkey, the tool we've developed. Like so many great ideas, it was born at a local bar, sitting around talking about new and current exploit conditions. So we had a few goals in mind for what we wanted this tool to do, to help not only ourselves, but our analysts and the community at large. And that was, we wanted a central database for collection and analysis. We wanted to be able to spider the web, finding new and interesting JavaScript, both benign, malicious, and everything in between. We also wanted a good way to collect these things. Not only a place to hold them, but a good spidering mechanism to hold them there. And we found those, which we'll talk about soon. We also wanted a good mechanism to feed in these collections into various browsers and collect the results. But most importantly, we wanted a safe and lightweight alternative. Because right now there's a lot of different ways that people are going about analyzing these malicious JavaScripts, but they're not really that safe. They go from really benign or really naive approaches, such as wrapping in a text box or text boxed area, where it'll just write the output of the JavaScript function into there, to other really heavyweight approaches, such as having VMware images and running all kinds of behavioral analysis on that. So we wanted to split the difference and be able to have something that the individual analyst could use without a lot of upkeep and trial and doing away with new images all the time and starting over, along with it being safe. So thankfully, we had a lot of great open source software to build on. SpiderMonkey, which is where the name for our tool comes from, it's the JavaScript engine for the Mozilla project. It's a great piece of code. It's gotten very mature because it's been being built in one way or another for the better part of 10 years and more, and rewritten over that time, of course, here and there. But it's a very mature piece of code, very heavyweight. You can do whatever you need to extend it. If you wanted to put JavaScript scripting into one of your applications that you've just written, you could easily do it. Provide your own DOM or anything else for it to script. You could drop SpiderMonkey in line and just deal with it directly through scripting instead of worrying about coding C all the time, which is kind of a good functionality. We also had the Heritrix web crawler from the good people at archive.org, another very mature piece of software. If you need to crawl websites to gather statistics or info, this is a great tool to look at for doing that. It's a lot better than the LWP script you're going to hack up in Perl. It's had a few more years under its belt to really get mature. And the good people at University of Michigan for some of their Perl and PHP scripting to pull out these archive files and easily allow us to analyze them and dissect them in various ways. So we're going to release this open source database and scripting released under GPL v3. SpiderMonkey extensions released under GPL v3 also. Basically, so that's the good news, and we hope that the whole community will take it and run with it from what we've already done. But basically what we did is a lot of wrapping and logging functions in the interpreter. We kind of split the difference between actually stepping through the code in a debugger and just doing behavioral analysis. We've kind of given it sort of a sandbox place where it can run and not have to deal with any crazy errors that it might come about or anything of that nature, but also to allow it to be run very speedily and accurately, and log the output for statistical analysis. Here's a demo screen. Here's the Heritrix web crawler. You can see a couple of jobs being worked. We ran more than a few to get our samples to start off with, and run some more since these slides have been created. And it's very consistent, very quick, and just provides a great platform. Here's another example screen of this.
Basically, what you're looking at on this screen is in Heritrix, it has the concept of crawler jobs. And so we went in and we defined some crawl jobs of places we thought we'd find some interesting samples. The first major crawl was of myspace.com. I believe what we're looking at here is the crawl report from our MySpace crawl. And you can see the vast majority of documents, or the vast majority of content that was retrieved was of a MIME type text HTML. There's a lot of JPEGs, a lot of GIFs. But what is interesting is we collected, about 400 or 500 unique JavaScript documents identified by MIME type across that crawler run. And so this is just kind of showing you the kind of graphs that you're going to see when you're running these crawl jobs through the Heritrix administrative front end here. And just to go back one real quick, what you're looking at here then is completed jobs, completed crawl jobs through the Heritrix front end. And I don't know if you could really make it out, but we've got several candidates we had crawled trying to find some interesting things. We'll talk about those runs a little bit later. But I know you all want to see the output of this tool we're talking about.
So here's Caffeine Monkey, and since live demos are destined to fail strictly by nature, we've decided to screenshot to the better way to go. So here you can see this particular piece of fairly heavily obfuscated JavaScript that we showed earlier in the presentation. We pasted it in here to the tool, and it's sitting here waiting at the command line to process. Our tool all runs on Linux, should compile on any Unix system, but we tested on Linux, both Red Hat and Debian. So if you're having trouble compiling it, it's probably a problem with your distribution, because if it hits those two, it's covering most of the bases. But anyway, it's sitting there waiting. So we get a lot of output. It's very, very verbose at this point, because we just wanted to throw everything it was seeing out at us. That can be tuned down in the future potentially, but for right now it spits out lots of log files. As you can see here, this JavaScript is starting off by building a string up through string concatenation. Every time you see a new string, that's a new concatenation. And you're seeing what it's become. And you can see here it's building up a document write, see what it's putting in. And as it goes, you can really run some analysis and see what's happening here. This is building up something to write into the web page, and it's going to be something malicious, potentially. Here we see it continue some more. We've skipped quite a few lines here because there's no sense in looking at the same lines over and over. So you see the new string up at the top. It's pretty much the complete new string that's being done. It's after quite a few. And then you see a val is being called, and the parameter, or the document write, is the parameter being passed into the eval function. So here we easily see what's actually being evaled, what might just be dummy code to throw the analyst off, or anything else, because you're actually hooked in to the trace of what would be happening, or what is happening.